Welcome to part 2 of the Recurrent Neural Network Symposium. We are not only talking about recurrent neural networks, but also about other machines that learn programs and algorithms. I have such a pleasure, and it's such a great honor to introduce the next speaker, Mike Mozer. In the 80s, he was an early deep learning pioneer because he invented a method which is known as focused backpropagation, and it's about dealing with certain time lags, long time lags in sequences, where it worked really well. Then he also was part of the team which created the first neural stack machines, differentiable, end-to-end differentiable machines that had an external storage in form of a push-down automaton where you had differentiable operations for popping and pushing elements on and from the stack. And many people today are using similar or related types of differentiable computers. It's a great honor, Mike Mozer.
When Jürgen invited me to speak here, he encouraged me to talk about that ancient work I did, work I've long forgotten and pretty much everyone else other than him has forgotten. Instead, I wanted to talk about an idea I've been fantasizing about for an RNN architecture, an alternative to LSTM. You may have figured out it's not real smart to cross Jürgen. It's also not smart to promise to give a talk on ideas you haven't tested, especially when 2,000 people are in the room. I expected that by today my kick-ass architecture would just crush LSTM, and just to give you a heads up, it's not there yet. So this is going to be more of a, isn't this a cool idea talk, rather than a talk that impresses you with large-scale simulation results or throws a whole career's worth of research at you. But let me step back and give you one motivation for this work. I work in machine learning and education these days, and I'm interested in predicting student knowledge. So if a student is studying some material over time, and then they get tested later, we'd like to predict what information they'll have learned and retained at the test time. Or if they're in 2 courses and studying material, and at a certain point in time they wish to study, what should we recommend to them? What material will benefit them most as far as their learning is concerned? Experimental psychologists know a lot about the temporal distribution of study and how it influences memory retention. As anyone who's taken Psych 1 has heard, massed study where you view the material multiple times in close proximity, is not as effective as spaced study for long-term retention. So if you're tested at some point later in time, you would expect to do better with spaced study rather than massed study. And it's not that memory is as strong with spaced study, but it decays more slowly. So you see memory persisting for a longer time. Here's a totally different domain. I'm going to switch gears, and let's think about a domain like product recommendation, and I'll connect the two. Over many years, I hop on shopping sites and look for electronic toys, and at other times, I have to replenish my stock of lunch food. I love these lentils. They're really delicious. And every once in a while, I have an emergency that requires a quick purchase, like my water heater broke down, I have to find parts for it. And the question for product recommendation is, at this point in time, what should you recommend? The time scale and temporal distribution of behavior is critical for modeling and predicting many different human activities, not just the 2 I mentioned, but music selection, making restaurant reservations, posting on web forums and social media, gaming online, engaging in criminal activities, sending emails and texts. All of these are activities that are characterized by events in time, discrete events, and each one's associated with a time tag. The typical sequence processing tasks we do with RNNs, like language understanding, don't have time tags, And you might view them as a special case where the time tags are all equally spaced. But in these situations that I have on this slide, the gap between events can vary by many orders of magnitude, and those gaps are important. There's been a bunch of recent research involving temporally situated events, some of which was presented at the main conference. And I'll just sort of list work so people don't feel slighted. And if I forgot your work, send me an email and I'll put it on my slide. And this is only stuff from the last 3 years because no one remembers anything from more than 3 years ago. The approach we've taken is to incorporate time into the recurrent neural net dynamics. And we do this by defining a new type of recurrent neuron, like an LSTM neuron, and it leverages the math of temporal point processes, work that's been done by Lei Song's group. So let me tell you a little bit about temporal point processes, and then we'll return to neural net land. A temporal point process is a stochastic process that produces a sequence of event times. It's characterized by a conditional intensity function, and I'll call it h as a function of time, and the h should give you the idea that that's going to become a hidden unit. And an intensity is essentially a rate, the probability that some event occurs in some time dt divided by dt. So everyone probably knows about Poisson processes. Poisson processes have a constant intensity function, so the rate doesn't change over time. You can have an inhomogeneous Poisson process where the intensity varies over time. And what we've explored are Hawkes processes, where the intensity depends on the event history. They're self-excitatory in the sense that the intensity increases with each event, and you can see that on the red curve. So the blue dots are, the blue blips are events, and anytime an event occurs, the intensity rises, and then it decays over time. And this is using an exponential kernel. The models I'll tell you about have an exponential kernel. Hawkes processes have a bursty property, which is really useful for modeling phenomena like earthquakes and financial transactions and criminal activities. Just to give you an intuition about where I'm going to go with this, oh, I can't turn my head. Suppose the events are purchases of a particular product or a class of products, and the more purchases you make, the more likely you are to make them in the near future. What near means really depends on the rate of decay here. So the decay rate determines the time scale of persistence, whether it's a behavior or whatever's producing events here. Now look at h of t as a hidden unit's activation. It's a decaying memory of past events. It's like LSTM if the decay rate is incredibly slow, but unlike LSTM, it has built-in forgetting. So a Hawkes process, just more formally, here's a conditional intensity function that specifies h. It has a base rate, mu, a parameter alpha that specifies how much of a bump does the intensity function get when an event occurs, and then gamma, which represents for an exponential kernel, the rate of decay of the bump. There's an incremental formulation of Hawkes processes with discrete updates where you initialize a variable, and then every time an event occurs, you do an update. That update captures the exponential decay that's occurred during that intervening time, delta t. I'm going to add one little bit of notation, x, where x denotes whether or not an event has occurred. And now I can express this as a neural net, back in the universe that most of us are comfortable with, where h is a recurrent hidden unit, which accepts input from the layer below. A bunch of these units are in the network looking at different types of events, looking for different classes of products or different classifications of products. You can think of mu and alpha and gamma as neural net parameters, but I'm going to make this a little bit more interesting in a second. The other thing about this model is that it needs to have delta t, not as an extra input with a weight on it, but it has this special meaning in the model. It has a special role to play, and there's no trainable weight on that connection. So now we can observe this time series and predict what comes next. So here's some history, like some history of purchases of electronics. And given the model parameters, we can compute the intensity from observations. And given the intensity, we can compute the likelihood of another event in some window delta t that I've drawn here in red. And there's just a tiny bit of math you have to do to calculate that. I'll give this expression a name z, just because I'm going to flash another slide later that has a z on it, so you'll know I didn't cheat you. The key premise of our work, though, is that the time scale for a certain type of event may vary from sequence to sequence. So if we have a trace of my purchases and Jürgen's purchases, Jürgen's may reflect his obsession with water heaters, and he buys them over and over again, whereas I just had a short interest. Lady Gaga may be a fleeting interest of Sepp's, but she's my favorite, so she'll be a long time interest of mine. So we can't treat the decay rate, or gamma, as a parameter that we want to train by gradient descent. We want to infer a timescale gamma that's appropriate for each event and also for each sequence. Okay, so this is some sort of adaptation that has to be done as a sequence is being processed. So we're going to do Bayesian inference of this timescale parameter. We're going to treat gamma as a random variable and as a discrete random variable, because I don't know how to deal with continuous things, that can be inferred from observations. So we define a set of candidate scales, use a log linear set to cover a large dynamic range. We have to specify a prior on gamma. And then every time a given event, either present or absent, happens at a particular time, we can perform a Bayesian update where the purple term here is a likelihood that comes from the Hawkes process. There's that z I wrote earlier. So just to give you a feel for how this all works, just a picture. Here's a sequence of events. And here are intensity functions based on decays that are short scale, medium scale, long scale. And this last graph shows inference over gamma. So the horizontal axis is time, just like the other graphs. The vertical axis represents different values of gamma, and the coloring represents a probability density. So think about these as a bunch of little vertical slices, each of which is a probability distribution. It starts off with a uniform distribution over gamma, and as time progresses, it focuses on the medium time scale, and the medium time scale is actually what I use to generate the sequence that's at the bottom. So it's recovered the time scale of the sequence from the data. And once I've recovered that time scale, I can then marginalize over the time scale, multiplying those posteriors by the different functions, and I get an expected intensity function. Okay, that's going to be kind of the output of my system. So internally, it's modeling all these timescales at once, but then it just outputs its expectation over those things. Here's just another version of the same thing. So here's 3 different sequences that are at short, medium, long timescale from bottom to top. And then here's the inference of those timescales, and you can see sort of over the series that it's figured out the blue one is a short. It's hard to, I know you can't see those numbers, but from bottom to top we have short timescales to long timescales. So the blue sequence is a short timescale, the purple is intermediate, and the red is a long timescale. And we can compute the expected intensity for those timescales, and this was the actual intensity functions used to generate the sequence, and you can see there's sort of a nice match between them. So again, it's recovered the appropriate timescale for each sequence. I want to show you one last one of these little examples before I move to neural nets. I want to show you the effect of spacing. So I have three series again, blue series, purple, and red for short spacing, medium spacing, long spacing. And when you run Hawk's process, even though they weren't generated by Hawk's process, you see it recovers that the blue is on a short, the purple on a medium, the red on a long. And when you compute the expected intensity functions, you see decays like this, and it's probably too small to see. But if you look far enough out in time after those events have happened, like think of those as students studying some material, the strength of the red trace is stronger than the blue trace. So it explains this basic spacing phenomenon that spaced study produces more durable memory. So we're going to build a memory unit, an HPM unit, out of this. Essentially, it holds a history of past events, but it's building it at multiple time scales, but it's still doing something like LSTM in building a history. It has a persistence that depends on its input history, which is different than LSTM. It doesn't have an explicit input or forget gate like LSTM, and it captures continuous time dynamics through that delta t input. So I can now embed that in a recurrent neural net, and there are a couple other details you need to know to do that. But to explain the net, let's just start with a generic LSTM RNN, which has some inputs. These can be events, things like products I'm purchasing, and outputs. You want to predict what you're going to buy next. And then in between, we have a bunch of LSTM units. This is just the totally generic architecture. And they feed back into themselves as well. And I can just replace those guys by these Hawk's process units, and I can add these extra delta t inputs that have a special meaning to the Hawk's process model, and then run things. So I'm almost out of time. There's two data sets I'll tell you about, if I have time, that we've looked at. This is a study of students learning Japanese-English word associations. These are very long sequences, like 655 trials that the student was studying over many months. And the picture on the right is just some random graphics to confuse you. And the task of the model here is, given the study history up to a certain trial, predict, given the item that's studied next, the accuracy, whether it's retrievable from memory or not. And so just as a baseline result, if the students were right more than wrong, and so the majority class correct is 62.7%. A traditional Hawk's process beats that by a tiny bit. Simply predicting that the next answer is the same as the previous gets you up to 71%. It's able to see across items, whereas the Hawk's process can't. LSTM gets 77.9, and the Hawk's process model does a tiny bit better. It's not meaningful. If I add delta t inputs to LSTM, it matches. We've done another data set with, I think I'm almost out of time, with Reddit postings, and a third data set with Last.fm artist selections. And both of those data sets produced essentially the same results, where the Hawk's process model matches LSTM, but doesn't beat it. The only thing interesting in the results is that if I take the input or forget gates out of LSTM, it does much poorer than the Hawk's process model. So the Hawk's process model is operating without those gates, which are often considered essential. And so it gives us a little bit of hope that the two models are picking up on different aspects of the input sequence. So just to finish up, human behavior and human preferences have dynamics that operate on a range of time scales. And so it seems like a model that's based on these dynamics should be a good predictor of human behavior, and hopefully also a good predictor of other time series that have multiple scale structure. The key idea of our model is to represent memory of sequences at multiple time scales simultaneously, and then output the appropriate time scale based on the input history. What we found so far, LSTM is pretty darn robust. There's some evidence that the HPM and LSTM are picking up on distinct information, as I said, and if so, there's a possibility that mixing unit types will obtain benefits. I'll know in a few weeks. And we're also considering other types of units that are premised on alternative temporal point processes, for example, self-correcting processes, which are useful for representing both periodic structure or some sort of satiation of interest. If you've just had dessert, you're probably not going to want another dessert for a while. So, thank you very much.
Thank you. Oh, sorry. Thank you, Mike. Are there any questions?
Hi, thanks for the talk over here. Yes. I was a little confused about the relationship between like the inputs and the units. So is it the case that like every unit is supposed to represent some kind of input, or how do you actually do this inference that?
It's an ordinary input to hidden layer connection. So the job of the model is to learn to discover events in the input vectors. So I use a localist representation of inputs, and it can pick up on what sort of groupings of those inputs should go together as part of the same event. So we've done experiments where, for example, we had several musical artists who were equivalent to a user, and it learns to group them together and predict not a specific artist, but a class of artists. So it's doing all the usual benefits you get out of neural nets, which is discovering representations, which an ordinary Hawk's process model wouldn't do, because you'd have to assign each memory cell to one particular event.
But so the events in a Hawk's process would be discrete, but if you have an input connection, you have like real valued inputs to your Hawk's process units?
So far, all we've done is to look at discrete events that are one of n events. So I can't say anything about other sorts of inputs. In principle, there's no reason why you can't give it distributed vectors and have it still figure out what constitutes an event in the input, or some combination of events in the input.
I try.
Thanks. Honestly, I'm still a bit confused, but maybe I'll ask you later.
Sorry.
We have to move on. Let's thank Mike again.